Hello students, in this video we are going to see dimension and rank. Dimension and rank. Okay. First of all we see one theorem. Let B is equal to matrix B1 bar, B2 bar and so on up to Bk bar be a basis for a subspace H, then every vector in H is written in only one way as a linear combination of the basis vector okay. Proof. First we understand what is statement of theorem. We have given B is equals to B1 bar, B2 bar and so on up to Bk bar be a basis for subspace of H. This set is basis for subspace of H means first of all this set B is linearly independent and second one is B spans H. B spans H means what? Every vector in H can be written as linear combination of set of vectors in B. That is, if V bar belongs to H, that V bar can be written as alpha 1 into B1 bar plus and so on alpha 2 into B2 bar. Okay students? Then every vector in H is written in only one way as a linear combination of the basis of vector. Here we have to prove that every vector in H can be written as in only one way as a linear combination of basis of vectors. Means here if we have taken V bar is equals to alpha 1 into B1 bar plus and so on up to alpha k into Bk bar. And V bar is also, suppose we have taken another linear combination of beta 1 into B1 bar and so on up to beta k into Bk bar. Then we have to show that this alpha 1 is equals to alpha 1 is equals to beta 1 and so on up to alpha k is equals to beta k. Means every vector in this H is written in only one way as linear combination of the basis vectors. Okay. So now we will prove this. Let U bar be any vector in H and suppose U bar is expressed in two ways. As linear combination of B1 bar, B2 bar and so on up to Bk bar. Suppose U bar is equals to alpha 1 into B1 bar plus and so on up to alpha k into Bk bar. Okay. And also U bar can be written as beta 1 into U1 bar plus and so on up to beta k into uk 1. Okay. Then subtracting and using properties of vector addition, and scalar multiplication, we get, subtract this vector u bar minus u bar. Here u bar is alpha 1 into b1 bar plus and so on up to plus alpha k into bk bar. Okay, minus beta 1 into u1 bar plus and so on up to plus beta k into uk bar. Okay. Student, here is b1 bar and bk bar. In first term, b1 bar is common, so take it outside, and in bracket remains alpha 1 minus beta 1 into b1 bar. In next term, beta 2 bar will be common, and in bracket remains alpha 2 minus beta 2 into b2 bar plus and so on up to plus alpha k minus beta k into bk bar. Okay. Since b is a basis for h, so vector b is linearly independent. Since b is linearly independent, the weights or scalars, students always remember that weights and scalars both are same. Suppose we call this equation number 1. In 1 must be all 0. Why? Because this set B is linearly independent. B is linearly independent. Therefore, we get alpha 1 minus beta 1 is equals to 0 and so on up to, okay, here I will write the 1 is equals to alpha 2 minus beta 2 and so on up to alpha k minus beta k, all are 0. Or here we will write which is equals to 0 and so on up to 0. So here we will get alpha I is equals to beta I, alpha I is equals to beta I for all I runs from 1 to and so on up to k. Okay. This shows that here in previous step we have written alpha 1 into b1 bar plus alpha k into bk bar, and your u bar is equals to also beta 1 into b1 bar plus and so on up to beta k into bk bar. Suppose this equation is star. Here alpha 1 is equals to beta 1 and so on up to alpha k is equals to beta k. So this shows that the two representations in this equation star are actually the same, which shows that two representations in star are actually the same. Are actually the same. Therefore, we can say that every vector in H is written in only one way as linear combination of the basis vectors. Okay. Hence, proof of this theorem is completed. Okay. Let us take next definition. Definition of coordinate of vector. Let B is equal to B1 bar, B2 bar and so on up to Bk bar be a basis for a subspace. H. Okay. For each x bar in capital H, the coordinate of x bar, the coordinate of x bar relative to the basis B, relative to the basis B are the weights of scalars, are the weights alpha 1, alpha 2 and so on up to alpha k, such that x bar is equal to alpha 1 into b1 bar plus and so on plus alpha k into bk bar, and the vector in Rk. It is denoted by x bar. This notation means coordinate vector of x bar relative to the basis b bar, which is nothing but the scalar alpha 1, alpha 2 and so on up to alpha k. Okay. It's called coordinate vector of x bar relative to the basis B, means relative to basis B, or the B coordinate vector, Students, definition is very simple. Let B is equals to set of all B1 bar and so on up to Bk bar be a basis for subspace H. Basis means what? This set is linearly independent and every vector in H can be written as a linear combination of B1 bar, B2 bar and so on up to Bk bar. Okay. For each x bar in H, the coordinate vector of x bar, take here capital X bar, relative to the basis B are the weights alpha 1, alpha 2 and so on up to alpha k, such that x bar is equal to alpha 1 into b1 bar plus and so on plus alpha k into bk bar and the vector in rk. This is denoted by, this is nothing but coordinate vector of x bar relative to the basis b. Okay, which is equals to alpha matrix alpha 1, alpha 2 and so on up to alpha k. Okay, let us take example on coordinate of a vector relative to basis b. Okay, example first, let b is equal to matrix 1 1 comma matrix 2 minus 1 be a basis. In this first part is if the coordinate vector of x bar is relative to the basis b is matrix 3 2, then find x bar, then find x. Second sub question is if the coordinate vector of u bar is coordinate vector of b relative to basis b is minus 1 3, then find u bar. Okay, and last one, if x bar is equals to vectors 4 5, find the coordinate vector x bar relative to the basis b. Okay, now we will solve one by one. In one, we have given coordinate vector of x bar relative to the basis b is equals to 3 2. First of all, we recall the definition of coordinate vector